I'm now ready to go beyond two variables and examine multiple variable relationships. Specifically, we're going to continue to have one response variable, but we're going to have more than one explanatory variable. All of these variables are going to be quantitative in nature. Later on in the course, we will look at when we have categorical explanatory variables, and even later we'll look at a categorical response variable. But right now we're working with all quantitative variables. Now, the steps I'm going to take, which I've listed here, would fall under the umbrella of exploratory data analysis. That is not my favorite way to do things. It is, I will suggest, and suggest with quite a bit of confidence, the most common way that people look at variable relationships, but I don't think it should be. I think that with good science, what we should actually be doing is confirmatory analysis. That is, creating theoretical models based upon our understanding of how variables relate to one another, and from these models, then look at data and see if the model, in fact, corresponds to the data that we're observing in the way that we expect it. That would be my preference. However, the reason I am going to look at this from an exploratory standpoint, actually there's two reasons. One is that the exploratory way we're going to do this is actually going to cover the ways that you would deal with confirmation as well. And I'm going to bring that to your attention as we move along. So we'll come back to this concept of confirmatory. The second reason that I'm doing this exploratory is because I am talking to students and individuals who have very different discipline orientations. In fact, I'm even going to be looking at data that's not within my field of study. And so as a result of this, I would not necessarily know, in fact, I'll go stronger than that, I do not know how to create a confirmatory model. Let me show you a little bit about what I mean by actually looking at an example. And I'm going to start by looking at my notebook for a report that I'm going to construct. This report is going to model the number of physicians in small cities in the 1980s. So I've pasted in a question here for myself to answer. The health data from small cities are from a sample of United States cities in the 1980s. So this researcher selected a sample, I don't know if it was done at random, but let's assume it was, of small cities. I don't know what the definition was of small cities. It was actually in the book that he published about this, and we could go back and look. But what I'm going to do is write a report to study the variables that influence the number of physicians in a city. That is, why did some small cities have more physicians than others? What is responsible for that variation in the number of physicians? I'm going to include in the report a quote-unquote best model. That is, I'm going to look based upon the data for a model that seems to work well, analyzing both the descriptive and inferential characteristics of the model. All right, before we go further, let's take a look at what the variables are. We have a variable called doctors, which is the number of physicians per 100,000 residents. We have hospital beds, which is the number of hospital beds per 100,000 residents. We have income, the annual per capita income in thousands of dollars, and you'll be able to see when we look at income that this was from quite some time ago. And we have density, that is the population density per square mile. I also have here a reference to the book if you want more information. So I have one response variable, that is doctors, the physicians per 100,000 residents, and three possible explanatory variables. I say possible because I don't have to use all of these. Now, if this was actually my field of study, and I had these three explanatory variables, I could, in fact, propose a model based upon my theoretical knowledge of how small cities operate and the economics and the things that influence medical care and so forth. I could propose a model, and then we could potentially confirm that model. Now, we're going to keep it quite simple here, but let me go ahead and show you what I mean by that. So our response variable here is going to be the number of physicians we have. We'll call that doctors. And then we have three potential explanatory variables. And our simple model that we're going to start with later on in other units will get a little bit more complex. But our simple model that we're going to start with is looking at the possibility of any of these three explanatory variables or some combination of those influencing the number of doctors that go into the city. Now, we're not doing this as an experimental study, so this is a potential cause, not a confirmed cause. And when I talk about a possible confirmatory model, and I have these three variables, if I knew something about this subject matter, I might propose theoretically that I want this two-variable model right here because that's the one that makes the most sense, and then I see if this is a good model. Or I might even propose that really the best model I could have would just be this one, and I see if it is a good model. What we're going to be doing is more exploratory, in which we're going to allow the possibility of any combination of these three variables being a good way to predict the number of doctors. And we're going to do it based upon the data. That's the opposite of what I would do if I was doing confirmatory analysis. In a confirmatory sense, what I would do is propose the model, collect the data, see if my observations fit well with the model that I proposed. Instead, what we're doing is we're starting with the data, then we're putting in these variables and seeing if we can find the best model. Now, you might think that has quite an appeal to it. Why not? Why not go ahead and just use the data to find the best model? Well, consider that we start with a population and we draw from this a sample, and that from that sample we make our observations. We see our various data points. And then we utilize that information to create what we think is the best model to predict doctors. And another researcher comes along and draws a sample of data and then creates their model. And their model may, in fact, be quite different from our model, both in terms of the variables that they end up with and in terms of how well the model performs, how well the model fits. Why? Because they got a different sample. The models can change from sample to sample to sample. From a scientific standpoint, it makes a whole lot more sense for us to create a theoretical model based on our understanding of the variables and the interactions of those variables, and then see if, when we draw a sample of data, it fits. And if we want to be even more empowered in talking about fit, draw another sample and see if we get the same kind of results. See if, in fact, this would cross-validate across various samples. By taking these individual samples and creating these individual models, we're simply finding a model that is the best model for the data that we happen to have in hand. For exploration, for beginning understandings, fine. But realize that if you do that, then you're probably going to want to cross-validate your models or take other samples and see if you get the same kind of results. I think deep thinking and understanding about the variables you're working with, if we were doing this in a field that was our primary interest in our primary study, would be far more valuable. That said, the statistical techniques we're going to use in this exploratory analysis will give you everything you know for confirmatory analysis, and I'll come back to that later on. So I just want to give you that disclaimer as we start on this particular journey together, that we're going to be looking for a quote-unquote best model, and notice I put it in quotes on purpose. We're going to be looking for a best model here, and we're calling it the best model because it's the one that we come up with that we think works well with the data we have. Now, we're not just going to look for the best fitting model. We are going to take into account the fact that we would like as simple a model as possible. That is, we would like parsimony. And if we can do just as well with one variable as two or two variables as three, we're going to take advantage of that. And I'll talk more about that when we talk about what it means to be quote unquote best. Okay? So that's really the setup for what we're going to do here. I'm going to go back and forth between teaching you general concepts and then exemplifying them. But right now, as we get started here, we're going to graphically and descriptively explore our bivariate relationships. That is, we're going to look at all the possible pairs of two variables at a time and see if what we can learn about the relationship of these variables before we get started. And then we're going to look at various linear models. Again, that's exploratory. I'd only be looking at one model if I had a theoretical basis. Various linear models using multiple regression techniques. We're going to see how the regression coefficients change for each of those models. We're going to see how the strength of each model, how they differ from one another, and which models are the strongest. And we're also going to have to make inferences because now we have a sample of data and we want to infer back to all the small cities from this sample of data. But inference relies on conditions in order to have validity. And so we're going to have to look at the conditions we need for valid inference prior to actually making those inferences. So that's the setup. That's where we're going from here. I'll see you in the next video and we'll get started on this report.